Okay, everybody, we are in Chapter 9, and Chapter 9 is simply entitled Third Look at ML. There is going to be one more look at ML, and that's going to be Chapter 11. I want to just reiterate a couple of things here. One is just the critical need um, to go through when the author is explaining these things and talking about the language and the features. It's just critical to go through them on your own. I always require that, right? When it's homework time, just give you a little nudge to make sure you do that. But it's true of really learning any language. You go get a book that you like, and the book starts going through stuff. You can't just read it any more than you can read a grammar book about French and think you're going to learn how to speak French. You've got to go through it. You got to practice it. You got to conjugate some verbs, all that kind of stuff. So just kind of a reminder here. And chapter 9 is not that big. It's got a few really dense ideas embedded in it, though. So we're going to try to hit those and articulate those as well as we can, given the slides and the material we've got to work with. Maybe in the future, I'll try to get, some better materials pulled together that will help to explain things a little bit better. But so what we're going to do here on this chapter, we got more pattern matching stuff, and some of the stuff is very, very cool. As we have found with ML, pattern matching is really, really awesome, and it just creates some really, truly elegant solutions to things. We're going to talk about function values and anonymous functions. And then we'll talk about higher order functions and currying, and that's the one that'll kind of blow your head just a little bit. And I'll reinforce again the criticality of when you're programming in ML or any functional language to just get out away from the normal kind of imperative, procedural, object oriented. You've got to change your mindset, or it will just mess with you. You won't let go of those things. And if you don't let go and begin to feel it and think it, you're just going to be in trouble. And then we'll talk about specifically three different higher order functions, which is map and fold-R and fold-L, which become very, very useful, and which are kind of classic functional high order functions in functional programming languages. What we're going to do here is just kind of dive into the first couple of sections. No, the first section in the book. There is a section 9.1, which is just a very short introduction. And then we get to 9.2, which is kind of where we dive in here with pattern matching. So, we did this one. Here's the example right here, right? Where we looked at function definitions and how we could do pattern matching. And as we sort of, walked through, the pattern matching things just turn out to be so incredible, right? This one, for example, it's really just an if then else statement if you have to think of it that way. But really, it's sort of an opportunity to say, if we match that pattern, we do that. If we match that pattern, we do something else. In either case, you remember we define a function, and we define the function differently. And so it's really like creating multiple function definitions and kind of binding them as we need them in as we're running, which is just a kind of a crazy idea. But there you have it. There's ML. So it turns out that there are some other kinds of expressions, one of which is this case statement. And we're going to kind of break this down just a little bit. It's quite interesting that, after going through all of this, I'll give you a little spoiler alert. The author says that you should use the case expression only when you need its extra flexibility. So there you have that. In this other case, these patterns were part of defining a function. For the case statement, you don't have to use that strictly in defining a function. So you do have, much like other kinds of switch statements that you might have in C++ or other languages, you've got that ability to just line up a set of patterns and use them, which turns out to be very handy. And again, the flexibility that they talk about in the book. So specifically, we're going to talk about what we call a match. And this really has kind of two parts. Again, we're going to go into some BNF here just to try to express that. I'd like to kind of maybe start more from the top, which is a match is defined as one or more rules and with this vertical bar, right? You think of it as the or sign or the pipe sign in Unix, followed by another match. And so what we can see, I'm just going to kind of jump ahead here again on this case expression, that we use this match where we've got the vertical bar that's separating them. And then specifically, we go back to the notion of a rule. So we've got individual rules. There's some pattern. There's this, just kind of a key token, really, just the equal sign greater than kind of the arrow. And then some expression. Again, going back here, what we see is, backing up, there's some rule. And then we've got a pattern, and then the arrow, and then the expression. So here's the pattern. And then that's what we're going to do. That's the expression, okay? Backing up again. And then this rule is basically defined as that combination of the pattern, okay? So the match is this whole thing, and the rule is, so these are a set of rules, okay? And so what's kind of important here, and it's fairly obvious, but all of the rules in a match have to have the same type of expression on the right-hand side. So over here, these all have to have the same kind of expression, okay? And I think if we go back, similar, these are really the same kind of an approach. If we go back one slide, these are the same kinds of expressions over on the right-hand side. And that's, again, relating to the rule and specifically the expressions. The match itself is not an expression all by itself. It's a chunk, it's a piece that can be used in different kinds of ML expressions. For example, the case expression. And I want to just say one thing about, we've got an example here of a case, backing up again. On this previous slide, this case N of kind of 0, non-zero, to me has a certain intuition. I mean, and it's clear that dumping a string that says 0, non-zero is a placeholder for some other kind of logic, right? You should be able to see that. But I like this. It has a certain intuition. This one I just don't like because it illustrates the syntax, but there's no motivation to, there's just no reason, I don't know, to have case 1 + 1 of, and then, I wonder what that'll be. So I don't like this example, frankly. But it does serve to illustrate that you've got, some, what do we call this thing here? It's an expression, and based on how that expression gets evaluated, it can then match these over here, these values over here, and then that rule is going to apply, and this thing here is going to pop out the other side. Well, specifically that thing right there, the 2. Anyway, it does a lot of cool things, and there's a lot of things we can do with the case expression. I think we're going to see more of that as we kind of get deeper into ML, but this is just an introduction to that. What I think you can see is that it paves the way for more sophisticated kinds of control or decision-making kinds of things inside the function, not just at the point where the function is declared, right? And here's another example of that. And this one I really like. You should code this thing up. But here you've got a case expression. There's some value x. And then here's the set of rules. And what this does, I want to just point out something that can be a little bit confusing. And there's some spots in the book, frankly, that are a little bit confusing relative to this apparent const operator. And I want to just say something that's kind of critical here. We have this notion of a const, right, which is the 2 colons stuck together. And we know we can take a const and use that to take an element on the left and a list on the right, and you can append that element, kind of like add it to the list, put it inside the list, right? And but we don't have, this ability to do, repeated consts like that. This is not constructing stuff, and you gotta flip that in your head. This is not constructing things using const. This is using the const sort of operator as a method by which we can look at this and recognize the pattern. It's a way of just saying chunks of a list, okay? So really what it says is that if I have a list, and that's kind of the first thing this says, if I've got a list, and there's an element, the first one, the head of that list, and I don't care what it is, and the second element of the list, and I don't care what that is, the third element of the list has to be there, which means this is, this rule is only going to work if I've got 3 or more elements in my list. And then I'm just going to conveniently label this guy C. Well, in that instance, then what I'm going to return from this expression is C. Then alternately, there's my bar, alternately, I don't care about the head, but if there's a second one, so in other words, everything 3 or over is going to get caught here in this first rule. Everything, of what's remaining is going to be empty, 1 and 2, right? Duh. So in the case where it's 2, which I'm going to try next, I'm going to, again, ignore whatever the first thing is. And then I've got a second element. I don't care what comes after. It could be null or it could be something. But again, we've already handled this case. So what that's going to be is null. Well, then I've also given it a convenient name, which is B. Alternatively, if I've got a head and I don't care, then I'm A. And if it's nil, then I'm just 0. Okay. Okay, what's really interesting and what's so cool and powerful about pattern matching in ML is it not only just kind of shows you, there used to be a thing called query by example. It was sort of like how to do a SQL query, but instead of having to do what you do with SQL, it basically just kind of gave you patterns. You'd have to match a pattern. If you match the pattern, you could go do, you'd get the results back. And I always really liked query by example back in the day. I don't even know if it still exists, but it certainly didn't become the big thing for a number of reasons. But anyway, just want to kind of point out again that this idea that the pattern is right there staring at you. Something, something, and then something I don't care about, something I don't care about. And then the third item is something I do care about. And ML just says, why don't we just call that C? Now you can talk about it. Okay, then I can do whatever I want. I can multiply it, change it, just do whatever, but I know what it is. And that's kind of what this is sort of, kind of expressing. And then just to kind of, again, drill this idea home, the case expression is really a generalization of the if statement. It's really an if then else, okay? What happens with an if then else is if there's an expression, it has to evaluate, right, to true or false. Then there's another expression which has to evaluate to true or false. And then if this is true, then, this one, let me back up. If this first expression is true, then we perform the second expression. Otherwise, we perform the third expression. That's really kind of what's going on, okay? And so what's really happening here down in the case expression, I have this case, and here's my expression. And essentially, if that expression evaluates to true, then this rule would say, do expression 2. And if it evaluates to false, then this would say, do expression 3. What I'm just trying to kind of illustrate to you after messing up that explanation, what I'm trying to illustrate is that this if then else idea is identical in structure to this case expression. And I hope you can see that. That really kind of just reinforces that. So really, as this slide points out, the if then else is really just a special case of the case expression. So that's going to be what we're going to do on the pattern matching. On the next podcast, we're going to come back to the function values and anonymous functions.